In 1803, the brilliant scientist John Dalton was able to prove in the lab what the ancient Greeks thousands of years earlier thought might be true, that matter was made of incredibly tiny building blocks called atoms. Dalton thought that atoms were solid spheres like billiard balls, and that they were the smallest particles in the universe. But about 100 years later, scientists discovered that atoms were made of even smaller particles. This video shows how they were able to do that. In 1897, a clever Englishman called J. Thomson designed a glass tube filled with low-pressure gas and containing two metal plates inside. When he put a big electric charge on the plates, he found that the positively charged plate, called the anode, was able to pull a beam of tiny particles out of the negatively charged plate, called the cathode. Because the beam came from the cathode, he called them cathode rays, and he called the apparatus a cathode ray tube. You can see the beam as a blue line in the diagram. Where the cathode rays arrived at the anode, there was a little hole that allowed them to travel through and continue and pass between a pair of parallel plates that he could put varying charges on. Sometimes the top one was positive with the bottom one negative, and sometimes the other way round. The beam always bent away from whichever plate was negative and towards whichever plate was positive. This meant that the particles must have carried a negative charge, because we know that like charges repel and unlike charges attract. But here's the thing. Because the beams bent so easily, more than other particles going through the plates, he could work out that they must have been very light, thousands of times lighter than a hydrogen atom. Thomson realized that atoms had even smaller particles inside them, and that they carried a negative charge. He had discovered the electron. He won a Nobel Prize for this. J. Thomson was not only a brilliant scientist, he was a really good bloke as well, and he helped many of his students become famous scientists too. 7 of them went on to win the Nobel Prize, including his own son. One of his students was Ernest Rutherford, an extroverted New Zealander with a booming voice and a big laugh. Rutherford was playing around with beams of positively charged particles, which he called alpha particles, that were emitted from uranium atoms. He knew they were positively charged because they bent in the opposite direction to the electrons of a cathode ray when passed through charged parallel plates. They bent more slowly than electrons, so he knew they were heavier than electrons too. Rutherford used these alpha particles as atomic bullets and fired them at a very thin sheet of gold that was only about 1,000 atoms thick. On the opposite side to the uranium source, he placed a scintillation screen that lit up when particles hit it, so he could then measure where the alpha particles landed. If the gold atoms were like billiard balls, then the alpha particles would be blocked and none would arrive at the screen. Instead, almost all the alpha particles passed straight through the gold foil, as though it wasn't there. Rutherford realized that the gold atoms were mostly empty space. J. Thomson thought that the mass of atoms was pretty evenly smeared out within the substance, and he also thought that most of the alpha particles would pass through. But something very surprising happened. Some of the particles were bent a few degrees off course, and about 1 alpha particle in 20,000 bounced right back in the direction from where it came. Rutherford said at the time that It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. What this meant was that the mass of the gold was not evenly spread out at all, but concentrated in very small lumps that were positively charged. He had discovered the atom's nucleus. Because the nucleus was so small, most alpha particles didn't even come close and completely miss them. They went straight through. If some went close to the nucleus, its positive charge would cause repulsion and bend them off course. If an alpha particle made an occasional direct hit, it would bounce right back from where it came, because the nucleus was much, much heavier than the alpha particle itself. The nucleus is incredibly heavy. Over 99% of the atom's weight is concentrated there, and incredibly small. If we magnified an atom to be the size of a football stadium, the nucleus would be the size of a pea. Rutherford later discovered a particle inside the nucleus that was responsible for its positive charge, and he called it the proton. An atom's overall nuclear charge was equal to the number of protons it had in its nucleus. And this also turned out to be the same as the atom's atomic number. Each element had its own number of protons in its nucleus. How's that for a coincidence?